So today I'm going to talk a bit about VM and JIT profiling in VAST and how we use tools here to simplify the job of investigating performance issues in the VM. So I'm going to do a short explanation of how the JIT in VAST works, and then look at the different challenges and solutions that we've encountered and the solution we've chosen to do it, and then I'm going to do a short demo to show how the tools work. So the VAST JIT, it was presented in ESUG 2019 by a colleague of mine. So the video is available on YouTube for those who are interested. It's based on LLVM, but it does not use the LLVM JIT library. That library is very good at highly optimizing code if you JIT an entire method, but it both has a large library footprint, and it also has pretty long compile times to get this efficient assembly. So, instead, the approach that my colleague took was to pre-compile all our bytecodes from LLVM IR into platform bytecode, platform machine code. So we have a file for each platform which contains all of the machine code that has been generated by LLVM from the IR instructions that define that bytecode. And then at runtime, we sort of just concatenate them together, copy them together, and then we patch in the values that are actually have to be different based on the context of the method. So at the time, I don't think I heard another method, another VM that did the same, at least not for JITting. But now Python has started doing the same. So this is from last year, I think, where they announced that they were doing a JIT. And if you read the post, it's basically a very good description of exactly the same thing we are doing. So this is a quote from the blog post. I think they might have the references incorrect, but they probably didn't watch the ESUG video. So yeah. So when you want to profile the VM, usually, I mean, we're okay with image side profilers, and we get nice sampling, we get a nice call tree, and everything works in most cases. But then, maybe it doesn't. So here, I'm trying to profile an expert at in a method of ours. And the samples that I get are kind of nonsense. I mean, there's lots of code in this method, but it's kind of maybe a bit hard to see. All of the samples here have been sort of assigned to wherever scavenges happen. So those are the only suspension points in that method where the sampler was able to actually collect the sample, because the rest is primitives, or it's sort of optimized bytecodes that don't have suspension points. And that gives the image side profiler a hard time of sort of looking into which parts of this method is actually taking a lot of time. So there are other edge cases as well. We use it for when we build a new VM. We have like you discussed the micro benchmarks. We have something similar, so we run those when we build the VM, and we check if there's been a performance regressions. And normally there isn't, so we don't really dive into the results, but sometimes we update LLVM and the sort of emission of our bytecode IR changes, so there might be some changes, either improvements, in which case we usually let it go, and if there are regressions, then we have to look into it a bit more. There's also some cases we've encountered where we've had the same machine code running on the same hardware, but with quite different performance. So that can be both because the hardware is the same, but they're running on a virtualization platform. So There are many settings in the virtualization platform that can affect how long each assembly operation takes. And it can also be security settings in the operating systems, like Spectre mitigations that change the cost of doing native calls quite drastically. Yeah. So when you want to profile the VM, the first thing is, of course, that profilers work with known stack frame layouts, like C frames for the most standard. And we don't really do that either in the interpreter, which is mostly a loop, or in the JIT, which is not C frames at all. It's just a compiled sequence of bytes that we jumped into. And yeah. So if you try to just look at the call stack in a profiler, it will look something like this. You might have a few method names without any debug symbols, which are the exported symbols, but everything else is kind of Greek. And there's also the highlighted blue one that is 71% of the runtime in this example, which is just unknown stack frames. And that's basically the JIT section, which has been sampled. So it is possible to emit debug symbols dynamically, but in that case, if you want to keep the standard sort of symbol format, you can't have the same location used for two different things. So you end up having to compile to one location only and not assign to that location again, which makes it a bit hard, the way we usually structure the JIT, where we fill it up and then we flush it whenever we GC or anything like that, and we sort of rebuild it from scratch. At least that's what we usually do, because the whole copy and patch operation is a very, very quick way of building a JITted version. So the solutions are, you can build your own tracing, like Gia demonstrated last year for Druid, or you can sort of hook into existing tools and leverage those. There are different ones for different platforms and different processors. So the one I'm going to demonstrate today is the Intel vTune JIT Profiling API, which is available for x86 and x64 processors for both Windows and Linux. And you also have a file format that was defined by Linus Torvalds to dump time-stamped information about which functions reside in which areas of memory at a certain point in time. So you combine that file with a normal like perf trace, and then it will sort of deduce from the samples that were taken by the perf tool which method was it referring to at this time. So yeah. Now it's time for the demo. And I have to change my computer, so I'm sorry if everything goes boom. So this is the method we were looking at earlier. It's doing quite a bit of things, but most of it is actually either inlined sends, like a do, or it's primitives, like the Unicode string add. So that's why we didn't really see a lot of different call sites here. So I thought I would just demonstrate what happens when you hook this into a vTune that has, oops, let me just turn off the sound. So this is a special build of the vTune that has been hooked up to the Intel API. So whenever we JIT a method, it records the name of the method that's been JITted, and it records the location of the region of each of the bytecodes that has been compiled. So when we configure the analysis here, we are launching a special version of the platform that has been compiled with the JIT trace and the debug symbols. But the image is exactly the same as was open here, which I had from the normal environments. So we usually want to start it here post, so we don't start tracing right away, because the image has to start first. But now we can select the sampler expression. We can say we want to start the collection and we want to execute the sampler. So once this one pops up, we're basically done. And we stop the collection of data. And then it takes quite a while to finalize the results because it's a lot of events that have been traced. So in this particular case, I'm doing this on an ARM machine, not on an AMD machine, not an Intel machine. So I don't know if you noticed, but in the analysis configuration, if I try to use hardware-based sampling, which also gives you access to cache misses and everything like that in the profile, then it would have failed because it's an Intel tool, and as long as you don't have an Intel computer, it cannot recognize this. Yeah. But it does let us use the normal sort of sampling for ARM processors, for AMD processors as well. So I do have a couple of other traces prepared, but I think we're about to have this one open. Yeah, so let's just, yeah. So if we go to the top-down tree, that's the tree we are used to from the Smalltalk type of profiler. And we have the same RTL user thread start that was in the other one, but all of a sudden we have all the method names. That's due to the debug symbols, not because we are tracing the JIT functions as well. Yeah, these are the VM functions. So actually I should close this call stack, because then you can see, if I remove this one, so you can see which module it's in. So this is the normal VA executable, and this is the DLL that sort of implements the interpreter and the JIT and everything. But here we get to the interesting part. This is what is labeled dynamic code. So that's what you get when you plug into the framework. So you can, if there are certain regions you're interested in, if you're under longer trace, you can select that and zoom in and filter, and it will remove all of the nodes that are outside. And you can easily say that, okay, I'm not really interested in the ESP sampler overhead, so I can just filter out by selection the sampling nodes, so you can focus on what matters. And you can sort of see all of the different things. So obviously, when you have lots of code like this, you don't get a call graph in the sense you do in Smalltalk, because we are still in an unknown frame structure. But it does recognize when it does the samples that which method was registered for this region, and also which program count, what bytecode was there. So if you want, you can either, right now we have it ordered by the total CPU time taken by each of them, so you can see which of the bytecodes was the most expensive in exptoll. Or you can order them by name, and then you get like the logical order that you would see if you inspected the bytecode in the compiled method in the image. So most of the time in this case is actually taken by this fun little internal continuous execution, which is where it does all of the lookups, but also sends all the native primitives. So we have, if we order by CPU time here, so we don't get the chaff. Most of this actually involves Unicode primitives. So you get a good sense of the distribution of the actual sense from the method that we looked at earlier. So yeah. Another interesting example maybe is benchfib, which is a standard benchmark method in Smalltalk. So this is just doing Fibonacci of 27, I think it is. There are other options to show here as well, but I'll just use the top-down view since that's sort of what we're used to. It has the same functionality where you can sort of, if you accidentally recorded some input events that you're not interested in, you can zoom out, zoom in, and filter them out. And you can see that in this case, we spent 86% in the fib colon method, which is the recursive call from Fibonacci. So, but more interestingly, you can also see which of the bytecodes actually had the most samples recorded. So obviously the accuracy of this would be even better if it was tracing, using tracing primitives, but it's still quite nice with sampling. So yeah. And the final thing I wanted to demo was the last case I was talking about, where we had two machines, the same machine with a different Windows setting. When you have two different traces, you can also compare the results. So you can see from one run to another what the difference is in runtime and how the two traces differ. So just using the same top-down tree, we now get an extra well, we get the same field, but instead of having an absolute value, it now has a relative value. So this one took 30 seconds longer than it used to. And if we go down here, we can see that most of that was in the save image primitive somehow. And then there were some other primitives that took a bit longer than usual. But also in the integer benchmark itself, there were some weird anomalies with some of the bytecodes that took 6 seconds longer in one trace than the other. So it's a useful tool to sort of pin down where you have to look if there's anything weird going on. And it's quite quick to use. So yeah, we found this a useful tool to have in your pocket when you need to look into the performance of VMs. And like I said earlier, if this had been an Intel machine, in addition to all of the tree nodes here, you would also have on the, well, yeah. Okay, there's supposed to be some stuff at the bottom showing all the threads, the one where I filtered and things, but maybe not for when you compare them. Maybe that's just when you have a single thread, single one, where you should also be able to see where the cache misses occurred and things like that. So it's a powerful tool that sort of helps you avoid having to build all of this sort of investigative scaffolding yourself in order to get the insights that you need. So, okay, that's the end of my demo. Well, it depends on whether or not it comes back. No, it doesn't. No, it's extended, but the demo isn't showing. Okay, here we go. Yeah, so there's one more slide. So, any questions?
Thank you. That was interesting. So, is VAST using a copy and patch?
Yes.
Is that what you were describing?
Yes.
That you were actually doing it, and then someone wrote it up, and
yeah, 3
okay.
years later.
Yeah.
After we presented it, but then it was already done.
Yeah, so. We're for Zag Smalltalk, we're looking at using a full LLVM jitter, but
yeah, like I said, I know my colleague investigated it, and he found it to be too slow to use for
yes.
a JIT in Smalltalk. At least.
So we might be interested in doing it as a multi-phase one using a copy and patch.
Yeah, so
as the first round. Obviously,
you get less optimized code because you're sort of doing an SSA form for each bytecode instead of each method. But
right.
in essence, it gave a good speed up over the interpreter that was also in LLVM. At a very low compilation cost. So it's very, very quick at compiling.
Right. The other question, but you use the LLVM IR writer to write your code.
So
you basically told it the instructions you wanted and then let it generate the JIT code.
We are sort of the code that emits the JIT is written in C++, so it uses the IR builder to sort of define the operations that are part of each bytecode. And then we actually have two versions of each, one for the interpreter, and then we build some scaffolding on top of that, which is needed for the patch-ups. And then that's what we sort of use when we stitch them together to become the JIT version of a method.
Okay, so I don't want to go too far down this path, but so essentially you tell it the instructions you want, and then instead of, okay, go optimal way to do this, you just go straight to now build the instructions. Is that?
Yeah, no. We use the IR. We as part of the generation phase of the VM, we have a defined set of IR operations. You know,
Okay.
so.
Thank you.
So as part of the build, we do the compilation from IR to machine code. I don't understand. Maybe I understood the question incorrectly.
Okay. Thank you.
Here. So I have a couple of questions, but so the first one is silly. So you said many times that you don't have a standard frame structure. So you're just not pushing the frame pointer.
Yes.
Okay.
Well,
Is that actually working?
We have a custom calling convention that my colleague also invented that sort of saves some of the stuff in registers, so we don't have to spill stuff to the stack and everything. But it's not the format that is recognized by any kind of normal profiling tool. So we looked into whether or not it was possible to define your own custom frames for any of the tools, but that's not possible. So this is sort of the thing in the middle. You get the JITted methods, you get the bytecodes, but you can't really get any call graph between them or anything like that. Which ideally you could if you were able to parse the stack underneath and say, this is my custom format. So.
Then I don't know if somebody else, but otherwise what I was thinking, wait. Yes, so what is the API of this VTune stuff? So because you are interacting with it to give it the symbols and
like I said, when we're in the JIT phase, we sort of for each byte we sort of read all the bytecodes that are part of the method that we're going to JIT.
Yes.
And we calculate the total size that we're going to need in order to store the JITted version. And then we also have the offset map into the for where each bytecode is. So I'm basically just notifying the Intel tracer API, which has a certain set of API. It's like 2 or 3 functions, I think. You can define 2 levels, so we used it for method and bytecode, but
the mappings.
Yeah. So you just inform him at this address with this length, you can find this method, and it's basically the same information you emit to a file in the format that you can use on Linux. So.
And the other thing, so sometimes with Pablo we were discussing that. So for example, in Xcode, the profiler in Mac, you can extend it with custom events. Like for example, you were stopping the profiler, the tracing manually, and we were thinking, okay, maybe you can, if you can actually export an event like, okay, the startup is finished, I'm doing this, and then that will appear in the profiler, and you can actually manipulate the data.
Yeah.
So have you explored with stuff like that?
Well, we don't support Mac at the moment, so I haven't really looked into that platform too much. It's mostly Linux and Windows that I sort of looked at the options
this
for.
thing doesn't support.
Intel does not. No, they have a. Well, the JIT part is part of a larger framework where you can sort of notify it with custom events as well. So it might be possible, but at that point they had a special API for the JIT, so I just used that. So yeah.
Okay, thank you very much.